Dr. James Case. I can see he's here already. And okay, great. So Dr. James Case is an associate professor at Georgia Tech and a principal scientist at the autonomous driving company Argo AI. Before joining Georgia Tech, he was the mining assistant professor of computer science at Brown University. His research has involved object detection, tracking, localization, 3D mapping, and benchmark dataset creation. Particularly, he has been a major contributor to multiple widely used datasets, such as COCO dataset and SUN dataset. He has received prestigious awards such as Sloan Fellowship and the NSF Career Award. And today he will share his recent work on HD map generation titled Trust but Verify, HD map change detection. Please go ahead, Dr. Hayes.
Great, thank you for the introduction and thank you for inviting me to the workshop. And hey, everybody, it's my pleasure to talk to you all today and introduce a new data set, a somewhat new task that hasn't really been studied very much. So I'm talking about maps, whereas this workshop, I think a lot of the talks so far have been about localization, for example. And I'm not going to talk about localization today. In some sense, this is about all of the great stuff you get when localization works and you have a nice map. But then what happens if the map is wrong sometimes? So, self-driving cars, level 4 autonomy, they rely a lot on localization to a map, and it's called an HD map often. I'll explain what that means. And this is all about what happens when that goes a little bit wrong. So maps can change is the unfortunate cause of all of this. Let's look at some examples of our fleet operations in various cities. This is Washington, D.C. And on the left, you can see a sensor front camera image from July 2020. And then a few months later, in November, we can see that the lanes have been changed. A double yellow line has been changed into a single solid yellow line. The dashed lane is gone. So that's not great if you have maps that represent the world in July and you drive one day in November and find out that you've lost a lane or something like that. Here's another example in Pittsburgh now where a crosswalk has disappeared, if you can spot that. And maybe that's not super important. I think the AV will be watching for pedestrians anywhere regardless. But that's another element of your map that has gone stale. Here's another example from Pittsburgh where within a few months the road has changed quite a bit. The lanes have shifted to the left here. Now there's this, if you can see my cursor, there's this area where you're not allowed to drive anymore. And another example from Miami, now there's a concrete median in the road that wasn't there before. It seems to have been a turn lane before. So if you were going to turn left, you might use that. And now, concrete. So you can clearly, you don't want to blindly follow a map here that tells you that this is a lane that you would use when it's not even a drivable area anymore. Here's a slightly more subtle example. It took me a second to find this. I'm just curious how hard it is for people to find these changes themselves. Here, the lanes didn't really change, nor the crosswalks. Instead, the lanes got a little shorter because of, I guess, traffic calming measures that these bollards were added, and then new lines were added to say that you can't drive near them, or don't drive over the bollards, please. A lot of these changes happen when the road is repaved. In this case, the road wasn't repaved. You can see that the crosswalk has the same old wear patterns as it did. They just added some new lines and some bollards. Another change, paint here was changed. And I think the last example from Palo Alto in this case, where this was a forced merge to the left previously, and now it's two separate lanes. Most of the changes seem to be traffic calming type measures these days, where you're losing a lane. That's when you're actually gaining a lane. In both cases, a bike lane to your right as well, although the bike lane behaves a little differently. Here, the bike lane comes out in the road, and here the bike lane follows the curb. All right, so this is just an unfortunate property of our world that these changes happen. Just another example in Pittsburgh, move barriers added. I'll skip some of these other examples. What we're not focused on for this work are temporary changes, where somebody puts a road closed sign in the road, or an arrow board, or even just like a tree falls on the road. These are changes that are, they probably don't belong in a permanent map because they're temporary in nature, although you say that, and then there's probably barriers like this that have been up for years near you that are frustrating you. So some of them may be semi-permanent. But another thing I'll say about these is that they're mostly thing changes instead of stuff changes, like construction barrels or road signs. So an object detection framework can be looking out for these things while the car is driving. And in this work, we're focused on stuff changes, things to the surface of the road, to the drivable area, paint changes often, just to define the limits of what we're looking at. So how often does this actually even happen? Is it so rare that we shouldn't really worry about it? I think you probably wouldn't think that after those samples I've shown you, because even if it's rare, you can't just blindly trust your map, right? It's actually sort of annoying. It's rare, so it's hard to get data for, but it's not so rare that you can ignore it. But we actually collected a data set through our fleet operations, and we couldn't find similar numbers like this anywhere else to tell us, how often maps go stale. And so our definition of a map going stale here is we're looking at a 5-month period in our various cities of operation, and we're looking at a particular spatial unit, let's call it a tile that's 30 meters by 30 meters arbitrarily. We're saying, well, what's the probability that in those 5 months that a tile that we visit frequently will change at some point, will have a map change? And the absolute probabilities are pretty low, less than 1% for any 30 by 30 meter region in any city. But you're visiting thousands of these tiles in an AV every day. Anyway, anytime over that 5-month period, it's likely that, you're going to run into some map changes in different cities. Another interesting property is that the northern cities seem to see more map changes than the southern cities or the warm cities. I think that sort of makes some sense, maybe, just because of the climate causing more difficulty in the northern cities. So again, what does this tell us? Well, it is something we have to worry about, but it might be a little hard to get the data for it. So I haven't even rigorously defined what an HD map is, and it could be a lot of things. So this won't be the end-all definition of it. But what it's not is a routing map like you would find on Google Maps, which understands where roads are roughly and understands how they connect roughly. In the case of Google, I think it knows sort of well. It might be able to tell you that these 2 right lanes connect to this highway or something like that. But they don't actually have lane geometry in them. Again, Apple Maps. Here's another example. Sorry, the recording just started, I guess. Or OpenStreetMaps. All of these are more like routing maps that they tell you the connectivity of roads, but they don't tell you where individual lanes are. Whereas in our data set that we've released publicly called Argoverse, or in other data sets like NewScenes or Waymo or Lyft now, they have HD maps that have lane level geometry. So I would say that's the critical distinguishing factor, is that they have lane level geometry and probably connectivity to go with it. But they have other attributes as well, possibly pedestrian crossings, maybe sidewalks in some data sets. In our data set, we have ground height as well visualized here. And Florida is super flat, but even in this part of Miami where we're visualizing, there's a little bit of elevation change here. There could be other things in the HD map, traffic light locations, anything you want to store there. You could say that your 3D prior for localization is in there as well, but we're not really worrying about that for this work. We're worrying about this vector map, you might call it, of all the lane polygons and all the metadata associated with those lanes, like the left of this lane is this lane, and the paint on the lane boundary is this type of paint, like double yellow or something like that. So we would like to know when this object, which is a pretty compact object, even for a whole city. That's the cool thing about these maps, is they're not huge because of their vector representation. When does it no longer match the sensor data that you're seeing? That's the fundamental problem. We're creating a first data set for that problem and creating some baseline methods that try to attack that problem. And HD maps, I think all the serious level 4 autonomy efforts, whether at Argo or Waymo or Cruise or Motional, use these type of maps to improve their AV performance. But we also see in the literature a lot of papers that have found clever ways to use these type of HD maps now that data sets like Argoverse and the Waymo data set and NewScenes have these maps. And we see that from the sort of beginning of the perception stack, like 3D object detection and tracking, to higher level tasks like motion forecasting. The map is certainly critical there. If you want to predict the future motion of an object, it's a safe bet that it will follow the map most of the time, not always. And these HD maps are also used in motion planning or in creating plausible simulation in a lot of upcoming papers this year. So I think we're going to see more and more work on these HD maps. So the entities for this particular work that we're focusing on for HD maps, again, there could be a lot of other entities, are as shown here in this table. The pedestrian crossings, the lanes themselves, and the lanes have a lot of different attributes, as you're seeing here, whether it's a bike lane or a vehicle lane, whether it's in an intersection or not, so on. We also have this notion of drivable area, which is a polygon that will encompass all the lanes and potentially a little more, like maybe the shoulder of a road will be drivable area, but it's not a lane. So there's also a polygon for that. And then we also have pretty high resolution ground height for all of these scenarios that I'll show you. And HD map detection is a relatively new task. So there's not a whole lot of prior work because HD maps were not even, there were no public data sets until pretty recently. But there are some, and let me elaborate on the different possible approaches to this. Again, there's one extreme that would say, okay, these map changes are scary. I don't even want to map at this point. I'll just build the map every time I drive. I don't think that's feasible. Even for a human, they have a hard time driving in complicated scenarios where they've never driven there before, so that they don't have some mental map. Imagine you're going through, the middle of Boston in some intersection you've never been in. It's stressful. You don't even know what lane you're supposed to be in. Is this lane going to turn left or go straight up ahead? I can't see it. It's too crowded. So I think we are going to be using maps for autonomous driving. Okay, so if we accept that and accept that, well, all right, we need to figure out when they've gone wrong, so the car can do something, stop, call for help, remap in real time, whatever that is, the next step is. Then how do we determine when it's gone wrong? Well, you could keep a bunch of metadata, additional data beyond the map itself. Like if you remembered all the LiDAR or RGB data that you had seen anytime you had driven before, then maybe your maps, checking for a stale map would be, check the LiDAR I'm seeing right now versus the LiDAR I saw a few months ago. And if it's different enough, then I'll say that the map changed. So you're not directly necessarily using this abstract map, you're using the sensor data. There's some downsides to this. One is that the sensor data is huge. Storing this at a city scale is enormous. Another issue is that the world changes all sorts of ways through seasons and lighting and all sorts of things that aren't map changes. So it's still a difficult task to figure out if the map has changed, even if you remembered your sensor data from the mapping run. But that's not the type of approach we're setting up. We're saying you have your map, that artifact, that abstract artifact, and you have current sensor data, and you're going to be forced to make the binary decision: is the map valid or not? You could have bottom-up approaches that take your sensor data and detect lanes. So it's sort of like real-time mapping, except maybe you don't have the burden of really trying to map everything around you. You're at least mapping the things that you can be confident about, and you can compare those to your abstract map and say that, well, I'm pretty sure this lane, next to me, I think I'm remapping it right now, and it doesn't match what I have in my historical map. So maybe my map has gone stale. So this type of bottom-up approach, I think, is plausible. We're not going to evaluate that. We're going to be using more end-to-end methods that look like this latest work, where we're going to have a deep network, take in some representation of the map, take in the sensor data, and make the binary decision directly. And that deep network under the hood is surely learning to do things like lane detection and lane paint type detection and so on. All right, so what's in our data set? Again, TBV for trust but verify. So here's what our Z1 vehicles look like. This is where the sensor data comes from for this data set. The LiDAR in the data set comes from two 32 beam LiDARs spinning at 10 hertz, similar to what we already have public in the Argoverse data set. We also have 7 ring cameras taking 20 frames per second imagery. Each of these cameras individually has a global shutter, which will fire when one of the LiDARs sweeps above it. The LiDARs are 180 degrees out of phase. So they're individually 10 hertz, together they're sort of 20 hertz if you consider them as separate entities. And so every time one of them sweeps over a camera, then the camera fires, so you have synchronized LiDAR and camera imagery. And here's the type of map changes that we have collected into our data set and that we're going to try and detect. There's a lot of them out there, from crosswalk changes to lane geometry changes. Lane paint can change in all sorts of different ways. And again, I'll emphasize, we're looking for stuff changes, not things changes. So new stop sign, not in this data set, not in this task. Traffic light was moved, or there's a new left turn signal on the traffic light suddenly. That's not in this data set. Or the speed limit was changed. It's more like an object detection type task to look for those things. And this data set that we've assembled, this TBV data set, ends up being pretty hefty. It's 20 hours of data spanning 1,000 different scenarios. 200 of those have HD map changes in them, and it spans 6 cities. So it's it's pretty large, arguably the largest self-driving data set. Although it's not really comparable to these other ones because it doesn't have, for example, object annotations like the Waymo Open data set or the Argoverse tracking data set. And in fact, it only has low resolution video available because otherwise that would be an enormous amount of data. Here's just an example of, I'll pause this so it's not so jarring while I explain it. An example of what these scenarios with map changes look like. So on the left is the front camera image. And in the middle is some rendering of the abstract map that we have, of this vector map. It's not the only way you could render it. It's just the particular way we use for this paper. There's probably better ways to render it. But this is going to be an actual input to a deep network along with this. And on the right, you're just showing if they've blended naively. And this can help you notice some mismatches. And in fact, so this map, now it's saying mismatch. That's the ground truth, saying that this map is wrong right now. Why? Because this new lane got added. As it go forward a little bit, and you can see it more clearly. We lost the right lane. What else should I say about this? Yes, what you're seeing, why it looks jumpy, is we're sampling every 5 meters through these scenarios. So the scenarios are a mix of matches and mismatches. So now we've driven past where that lane was changes, and it's back to matching now that HD map is correct. And I'll show just a few more of these scenarios. You can see that the ground truth matching and mismatching is changing. Here it's the same thing. We lost the right lane in a different place, in different weather conditions. This is also Miami. And through this whole road, there's a map mismatch because of that right lane change. And sometimes, even for a human, it's really subtle to figure out, well, why is this map different? Here, a dashed line has been changed to a solid line, for example. And here, there's a new median on the left. We saw that example before. So the map doesn't even contain that. That's supposed to be a traffic lane there. No, it's concrete median. All right, so there's hundreds of these, and each of them has hundreds of, you could say individual frames of matching and mismatching maps. All right, so how do we train a method that will be good at comparing the map and the sensor data and saying that, okay, something's a little off with this map, given the sensor data that we have, and we're checking every 5 meters. We're building our training and test sets by sampling every 5 meters through these scenarios. Well, okay, let's look at a particular example. So here again is our HD map of some region of Miami. We're going to look at this intersection right down here. Our AV, approaches it one day and finds out that the map has changed. Again, it's sort of subtle to figure out, well, what's wrong with this map even? This is a bird's eye view projection of the RGB imagery, and we can do that pretty well because we have ground height, so we know where to project all the pixels. This could be cleaner. Again, it's just how we render it. It's not like necessarily the optimal way to render it. But what happened here? It looks like that they put some new cutouts on the sidewalks to improve accessibility, and at the same time, they made crosswalks between those cutouts. And those were not there before, and they're not there in the map. So there should be a crosswalk here and a crosswalk here. The map doesn't contain them. So this map is stale now. This is a mismatch. But again, it's a difficult machine learning problem to take these two things as inputs and to say that, oh yeah, this map is stale. So we could try to do that in bird's eye view, as I just showed you, or we could try to do that in ego view. Here's the same scene, but now from just looking at the forward camera perspective and looking at the map rendered from the forward camera perspective of the same scene in Miami. And I guess it turns out it's probably a little easier to do it in this viewpoint, actually. But we try both. And we try a few different architectures shown here. We try early fusion architectures where we take our sensor data and our map data, or a rasterization of our map data, and we just concatenate them and pass them into a traditional convolutional neural network. So this might be RGB, and this might be 5 layers or 10 layers, depending on how many different layers we're putting in the map. And they're concatenated, and at the end, you're just making a binary decision. This map is valid or not. We might additionally add something like semantic information from a semantic segmentation network that is trained to look for lane boundaries. When we do, it turns out that that helps a little bit to have that additional input. We also try late fusion, where a Siamese type network where we have 2 CNNs with shared parameters, even though they're viewing different modalities, the parameters are still shared. That's commonly done, sort of non-intuitive, but it often works quite well. But this late fusion does not work as well for us, as we'll see. The early fusion is the better performer. And as a sanity check, we also try a map only input, which should not work. If you just have the map itself and you're not even seeing the sensor data, you shouldn't be able to say whether the map is stale or not. You're not seeing the sensor data, but it's a sanity check to make sure our data set isn't biased some way. Like, what if all the map changes were only an intersection? So just by viewing the map and seeing that it's an intersection and say like, oh yeah, something probably changed because it's an intersection, it might do better than chance. And luckily, that's not really the case. So we want to train these models to do this task. There's one more wrinkle, which is that I said we have 200 scenarios sequences with map changes, and they have many frames each where map changes are visible, but it's still not a lot of data to train on because the space of possible map changes is enormous. So even though we have real map changes in this data set, we're going to keep those in the test set for evaluating different algorithms. And for training, we're going to actually synthesize the map changes. That is, we're going to take a sensor image, in this case, it's a bird's eye view sensor image, and take the map. In this case, we know that this map actually does match. We know this is what we could call a positive example. These correspond, the map is not stale. But if we mess with this map in any way, then we create a negative example, right? We could delete a lane, add a bike lane, change the crosswalk orientation. We could do anything to it that's non-trivial. We expect the changes to be substantial enough, and suddenly we have a negative example. And that's what we've done there on the right. We've added a bike lane on the right, if you see here. And so suddenly these two things together are now a negative training example, an example of a map change. And the reason that this is possible, again, it's hard to change, it's hard to make synthetic data in the RGB space. It's easy in this abstract vector map space, right? We sort of know the rules of maps. And so we can have heuristics to make changes to them that are plausible and generate a lot of training examples that way. And that's what we do. Here's another example. Again, at first glance, it's just to show you how hard this task is. So this map corresponds with this bird's eye view of this intersection. The rightmost one no longer does. Why? What even changed there to make that map stale? There was a lane marking that went from double yellow to single yellow down there. And so to do well on this data set, we're expecting you to find things this subtle. So it is a very hard task. Another example. Give guys a second to see if you can spot what changed. And it's a lane marking change. So white here means that there's a white lane marking, which indeed there is in this place. And red means it's implicit, like all of the lines through the intersection. It means that there is a lane there, but the marking is not actually painted there. And a lot of lanes on our roads are not actually painted. Another change. Here, a lane marking was deleted. Maybe this one is not as hard. You can spot that this lane marking is here and gets deleted there. And finally, here, could delete a crosswalk. This one's not so hard to spot. The crosswalk's gone. So this is how we synthesize map change examples. We also have plenty of positives. Normal fleet operations are just full of positives. So this is how we get negatives. And we train our method on those. And so this sort of could be thought of as a form of sim to real transfer. If we train on all those synthetic map changes, does it work when we try on those 200 held out test scenarios? The example, the big result is yes, kind of, but there's room for improvement, which is why I'm excited about making this data set public. So again, chance would be 50% on the validation set or the test set. The validation set is generated through the same synthetic map changes that we just described. So let's look at a real learning model. An early fusion method working in the ego view with all of the channels of inputs, RGB, semantic segmentation, map, on a validation set, which is the same distribution, the same synthetic distribution as its training data, it gets up to 84% accuracy, which is not bad. On the held out test set, it's only 67% accuracy, but that's if we're considering any change within 20 meters counts. But this is a ego view. It can only see forward. So if we evaluate it, so okay, only changes that you could have actually seen in your camera, then it gets up to 72% accuracy. Which is, still we would like that to be higher. Still, some of these map changes are very subtle. So this is not trivial to get to that level of performance, but I do expect there to be improvement if others attack the same task. And we can explore different combinations of modalities as inputs as well. I guess the simple conclusion is that more is better, and that the ego view works a little bit better, especially if you only evaluate it on things it can see. If you evaluate it on bird's eye view proximity, that is, you're responsible for knowing about any map changes around you, then they're about the same. So we've discussed this so far as just a binary task of saying, has the map changed or not? You could try to localize the changes in space. They're sort of localized in time right now, but they're not localized in space. We don't do that, but we do use visualization methods like GradCam here to show that the networks are implicitly localizing the changes. So if you see where the network's decision is putting weight to notice that there was a map change here, here's a sensor view, here's a map. You can see that the crosswalk is gone after they repaved this. You can see that in the sensor view, the network was putting a lot of weight here where the crosswalk used to be, and likewise on the vector map input. And just another example of that, where this road has been restriped. I mean, I guess there's one stripe there, but it's mostly just now, its lanes are mostly deleted. And you can see that the networks are putting a lot of weight on the relevant pixels. Hey, there should be paint here, the paint that I saw on the map over here. So we do plan to put this data set and the code and the pre-trained models online and to maintain a leaderboard on Eval AI. That's the competition leaderboards that we use for the other Argoverse challenges, and make this available for non-commercial use. And one more thing that I will tease at the end here. I mentioned the Argoverse data set, which is something that Argo has already released 2 years ago, CVPR in fact, that contains a sensor data set, a forecasting data set, and HD maps underneath each of those. We are releasing a new version of Argoverse soon, Argoverse 2.0. So I'm moving Zoom controls out of the way so I can see this myself, which will now span 6 cities instead of 2. We'll have a much larger sensor data set. We'll have new data sets in general, but one of them will be this data set I'm just discussing now, a map change data set, TVV. And all of these data sets will have new and improved HD maps underneath them. Okay, that's the end of my presentation. I'd love to hear questions from anyone.
Thank you very much. Thank you very much, Dr. Hayes. And one of the questions from the audience is, how do you treat visual changes of appearance which do not lead to a change in the map?
Right. So it is the burden of the deep network to learn that all of the changes that you see in the sensor data don't correspond to, it's different illumination. It's night instead of day. It's wet instead of dry. All of those things change the sensor data enormously, but they're not map changes. So in our case, we're hoping the network learns to be invariant to those things while still picking up on really subtle things like this went from a single yellow line to a double yellow line. But as we see from the quantitative results, there's still a lot of room for improvement there. I don't know if that answers your question. I mean, I basically just said we're trying to learn our way out of that. Maybe that's not feasible. I don't know.
So actually, you just mentioned illumination. Actually, that is in my mind as well. And when I do some research, and we found out in different time of the day, and the illumination is quite different. And for example, somehow a lane that is a pretty not strong lane, and in the very dark environment, and the illumination is not strong, and the lane may not be very visible. But in a very strong sunshine, and the illumination is very strong, and the lane is obviously visible. And how do you count those kind of illumination change into your change detection and in your HD map?
Right. The map representation that we're using in this data set, is abstract and totally blind to those type of changes. But I guess I'll agree that it's a challenge. And look at this scenario where, again, the sensor data has been spread out into a bird's eye view. But you see all of these almost phantom dashed lines that are coming from reflections from a building. So it's sunny and some building windows are reflecting onto the road below. And those reflections are stronger than the striped paint marks in some sense. That you can see one stripe there and one stripe there. So yeah, I mean, you're asking a lot of your machine learning methods to be able to distinguish all of these from actual paint. But the hope is that since it sees more than a terabyte of training examples of well, here's a matching map and here's a mismatching map, that it just learns to be invariant to these. But yeah, maybe it would be safe to say that that is the fundamental challenge here.
Okay, yeah, and I also noticed when in your fusion, early fusion and late fusion, And for the eagle view, you are using ResNet 18, but for the bird view, you are using ResNet 50. Is there a specific reason that you use different layers of ResNet?
It's just what empirically worked better. We tried all combinations, but yeah, the deeper model didn't help there. I don't know why. I mean, we could probably do something better and make the deeper model work better. It's not like we're short on training data, so that's not the issue.
Okay. So another one example, do you have examples of nighttime driving?
That is a good question. I would guess so, but maybe I didn't show any examples here of nighttime driving. I expect there are nighttime examples in the data set. I'm just trying to think back through all the visualizations that I've seen. It is, again, a data set that's so large that it's hard for a human to watch it all. It is 20 hours of data. I mean, this sort of sunset here, you can tell. So you're seeing reflections off the road. Just scrolling through quickly to see if I find night images. It looks like in this small sample, I'm not seeing any night images. But I think there are some in there.
So probably when the data set is released, and we can find out whether there's some quite a lot of data or portion of data is nighttime data. Yeah,
well, I can confidently say it's not a significant amount of nighttime data, but you know, I don't know, maybe 5% of it is night. I'm not certain.
Okay. Another question: do you use pixel-wise scan on final stage of forming synthetic samples?
So, okay, that's a cool question, the relations with GANs here. Let me go to one of these visualizations here. So let's see. So these are, that's not the synthesis example. Let me show a synthesis. So our synthesis is on the right. So we're synthesizing in this map representation, which is a little easier to synthesize than I claimed. You could absolutely have a GAN. You know, a GAN doesn't have to run in image space. You could have a GAN that's running in, you know, some other abstract vector map space, and that's telling us that, you know, here are plausible samples of maps, and here are implausible ones, and maybe that would get us a distribution of map changes that look more like the ones we see in the real world. That would be the goal, because if we're making map changes here that are totally unrealistic and we don't see in the real world, then it's sort of pointless training the model to catch them, because those aren't the map changes that actually happen. So you do have to worry about what that distribution of map changes is, and maybe something like a GAN makes sense to do that. We're not doing anything like that. And if we were doing it, I'm not sure I would do it pixel-wise on this. I would probably do it in some other representation. And there's also the left side here, this sensor data representation, which, you know, doesn't look quite photorealistic, although I don't know what a photorealistic bird's eye view is supposed to look like. It's difficult to stitch all the imagery together. And you could imagine trying to clean that up with something like a GAN, maybe. But no, we haven't looked into that.
Okay, cool. Actually, there's another question related to previously the question asked about illumination. And the question is, there a way that you validate the hope that the network learns invariability on weather conditions, so that you can obtain some sort of guarantee the system will look good enough under such under some conditions that are not so good? And what are the most challenging conditions you observe?
Right. So we saw that there were, for example, several rainy scenarios in the data set and several with low-level illumination. So those are certainly in there. The word guarantee is not something I would use here. I mean, I think we're going to see, you know, I hope to see, you know, over the next couple of years that these quantitative measures that we're reporting will see significant progress, so that, you know, test set accuracy is not 0.72, but it's 0.92. And then we get into the question of, well, is 0.92 good enough or not? You know, I don't know the answer to that. Yeah, I guess we could, you know, use visualizations like we have here, like GradCam, on more challenging cases, you know, with rainy weather and so on, to see that, you know, is the network attending to the right thing, where the right thing is, you know, the paint, and where the paint should be here, or where the paint has changed here. If it's attending to the right things, then we would have some evidence that we're learning to be invariant to those nuisance variables. Although I think, you know, if as quantitative numbers climb, and hopefully they do, then I think that it must imply that the networks are learning to be invariant to those nuisance variables.
Okay, Cool, thank you. And also another question about the sensors. And in the Argo OS autonomous vehicle, and we observe there are 7 cameras and facing in all the directions of the scene. And but we see quite a lot of data you are showing is actually front view. And do you purposely just use the front view in your data set, or there are quite a lot of other directions, like the side views and the back views also will be also incorporated in this data set?
Right. So all the views are there. And to build these sort of bird's eye view imagery that we're using for some of our experiments, it is using all 7 camera views. And the 7 camera views together do have 360-degree coverage. So yeah, all the data is there, although it's sort of low resolution because, again, it's just so much data. And the ego view one we do focus on a little bit because it works better. And it is the most important map changes are the ones in front of you logically, not entirely. It could be important to know about a map change that's to your right and in a lane that you're not even going to drive in, because that map change will influence the behavior of other objects that might interact with you in the future. But certainly the most important map changes are the ones you're about to drive on. So assessing it only in ego view, I think, is reasonable as well.
Okay, probably we have time for the last question. And for the sensors, and we actually also see there are 2 lidars, 2 32 beam lidars. And in the image you are showing, actually that are quite a lot. You are showing the image data, and will also the lidar data also incorporated in this data set, or somehow is mainly focused on the images?
Yeah, the LiDAR data is there in the data set, and it's extensively used. So in order to build those bird's eye view images, we have to use the LiDAR imagery to know, what the height of everything in the scene is, so that we can project pixels to the right places and things like that. So yeah, it's a lot of LiDAR data. I think it's going to be the biggest data set of LiDAR data when it's released. And yeah, it does have this somewhat unusual LiDAR arrangement. It's the same LiDAR arrangement from Argoverse that's already public, and it works well, although not as well. You might have seen that Argo publicized a new LiDAR that will be on our future vehicles. This is yeah, what we call the Z1 fleet vehicle. This is the LiDAR that it has.
Okay, and it's mainly used for changing from ego view to the bird view?
In our experiments, yes, although somebody else could use the data set and say, well, I'm going to use the LiDAR data directly. I'm going to build a LiDAR reflectance image from the LiDAR data, and I'm going to look for lane changes that way. And I think, that would be totally plausible.
Yep. Yeah, it does make sense, because from bird view, lane might be much easier to detect than the ego view in some conditions. Okay, I think time is up right now. And thank you very much again, Dr. Hayes, for your time. And we will move forward to the next speaker. Thank you. Thank you very much again.
My pleasure.
So,